Okay, so we'll go with just a nice dark blue here. All right. So our task is to solve polynomials. So like polynomials, remember I said lines were polynomials, right? So those are just what we would call linear. They're simple usually one-step equations. We can solve those. So if we have something like 3x plus 5, equals 12, that's a simple couple steps, solve it, right? If we have a quadratic, so something in the form of x squared plus 4x minus 8 equals 0. Most quadratics need to be set equal to 0 before you can solve them. There are some that don't have to be, but most of them do. All right. The easiest way to solve the way that works all the time to solve these is using the quadratic formula. So we're actually going to use the quadratic formula tonight. So that's why it's not a bad idea for just to take a quick gander at it. Okay, so the quadratic formula goes opposite of b plus or minus square root b squared minus 4ac all over 2a. All right, so that's what the quadratic formula. Most of you should be somewhat familiar, if not pretty familiar with it. All right, you saw it somewhere, probably in your math career somewhere. All right, so in the quadratic formula, a is always the first term here, so a would be 1 because we have one number. B is there, so b is 4. And c is here, c is negative 8. Okay, a, b, c. So it's the numbers out in front or just the numbers. Once you know what the numbers are, we're just going to fill them in, right? So wherever I see a b, I'm going to put a 4. Wherever I see a, I'm going to put a 1. And wherever I see a C, I'm going to put a negative 8.
Sorry, I can't tell in the formula that you wrote after B2. What does that say?
Minus 4AC.
Oh, it does say 4. Okay. Thank you.
Mm-hmm.
Oh, will you scroll back up a little bit? Sorry.
No, that's good. How far up you want me to go?
That's fine right there.
Okay.
And is that 4 constant? Is it always 4 AC?
Yeah, it's always 4AC.
It's been a while.
Oh, no, that's good. That's why we're reviewing it. Are we good? Can I go or yeah?
Yeah, you're good. Sorry, thank you.
Oh, that's okay. All right. So then normally we could just go ahead and put this in Desmos. Okay, I'm just going to run through it. Right, so 4 plus or minus 4 squared is 16. Minus 4 times 1 is 4. Minus that negative 8 gives me a plus 32. So I have this. And of course, this is just 2 on the bottom. Okay, so 4 squared 16. 4 times 1 is 4. Times 8 is 32. We have a minus and a minus, which makes it a plus. Okay, so those are my two answers. Negative 4 plus square root of 42 over 2, 448 over 2, and negative 4 minus the square root of 48 over 2. If you put those into a Desmos or a calculator or whatever, you're going to get decimals. Those decimals are most likely not going to be exact. It depends on how crazy that square root is. All right? You could get something that's, irrational where it doesn't repeat, doesn't terminate, goes on. You could get something that goes on for a little longer, but maybe stops. All right. Either way, this is always going to be your most accurate answer. All right. And the good thing about the quadratic formula, it works no matter what the quadratic is. All right. It's always going to give you an answer. So that's why we kind of push towards using the quadratic formula. You can solve them by factoring, but not this one. Okay, we couldn't have solved this one by factoring. There's only a certain amount of polynomials that can be solved by factoring. Not very many. It's like 10%. So I don't know if somebody actually did that study. That's just what they told me. All right, so this is a quadratic. All right, x squared plus 4x minus 8, set it equal to 0. I use the quadratic formula. A is 1, B is 4, C is negative 8. Put the numbers in, and here's what I get. Now, some of you are saying, shouldn't I reduce that 48? You can, but again, that's not going to change the answer. It's still going to be the same thing, it's just reduced. It's sort of like saying, well, should I reduce 6/8 down to 3/4? You can, but it's not changing the answer. 6/8 and 3/4 are the same thing. It's just you simplified it, all right? So yeah, you could break that 48 down, but again, it's not changing the answer. So we know how to solve a first degree and a second degree. What about a third? Well, there is no nice formula for a third degree polynomial, all right? There isn't. So let's take one, and I'm going to write it down here, and this is where I'm going to have you use Desmos. So you're going to be using some Desmos, again, pretty heavily tonight. Oh, this has got to be an x here, minus 12. All right? So we're going to set this equal to 0, and we're going to solve this. So here's how we do that. First thing you do is you graph it, all right? Because you could graph it and find those x-intercepts. So let's go find the x-intercepts, and let me know what you come up with.
Quick question for notes. So are you saying that the 3x plus 5 equals 12 at the very beginning of the notes is a first degree polynomial, and then quadratic is a second degree polynomial?
Yep. And this one's a third.
Perfect.
Good deal. Thank you. Okay, so -3, -1, and 2 are x-intercepts. All right, so x-intercepts and zeros and roots are all the same thing. All right, so -3, 1, and 2 are our solutions. All right, so we would write that there. There it is. It's solved. That's what x equals. Now, remember I said, if it asks you to write it in factored form, then you would go x plus 3, x plus 1, x minus 2. And remember that leading coefficient is going to jump out in front. All right? So that's what this would be in factored form. All right? All you're doing is changing these and putting them into the little x-intercepts form, sort of, with the x plus and the x plus and the x minus. But that's how you solve it. All right? So there are going to be some that you're just going to be able to solve by simply graphing them and finding the x-intercepts. These are nice x-intercepts, right? They're not all going to be nice, and that's where we might have to do something different. But in this case, everything's nice, all right? So questions on how we did that one? Just typing it in, graphing it.
I guess my question would be, how do you determine if you're just going to type it in and graph it to solve, or if you're going to put it into the quadratic formula?
Well, now you can't put any of these in the quadratic formula, right? This is a third degree. It doesn't have a formula.
Got it. So it can only if it's the second degree, can it go into the quadratic formula?
Yeah, I mean, you can graph it also and get the answer that way. But like if we would have graphed this one up here, we would not have gotten a nice x-intercepts. We would have gotten decimals. That would have been approximations. All right, that's what Desmos is going to give us. So we're really kind of after exact solutions in this case. But to answer your question a little bit further, you should graph these every single time in the beginning, because you don't know whether you're going to have a nice clean one like this or one that's not. All right, so that's done. All right, hey, we solved it. We just typed it in, got the x-intercepts, that's done. All right, let's try this one. X to the fifth minus 5x squared plus 2x plus 8. All right, so graph it again. I'm going to set it equal to 0, and let's see what the x-intercepts are, if there are some. -1, 2, and 4. You know, she's fast on that Desmos thing. There we are. So again, nice clean x-intercepts, right? So we could go x plus 1 for factored form, x minus 2, and x minus 4. But these are our answers, okay? That's what x equals. It's nice and clean. We don't even have a leading coefficient we have to worry about. That one's done. Windows. So what I would do is, if you go to Desmos, you'll see in the top right hand there is a little house. I would press the home key there, or home, however you want to think of it. What that does is it gives you a nice starting window. Most of the time, though, it's going to work.
Thank you.
Yep. Okay. So one of the things that we're noticing here is that we have a degree of 3, right? And we have 3 answers. So we have a degree of 3, and we have 3 answers. All right. So I want to go back and talk about something we talked about on Wednesday, and that is, if we take a third degree polynomial, it could have 2 x-intercepts. It could have 3 x-intercepts, or 2 x-intercepts, right, where this one's a double root, all right, or we even had that possibility where we could have 1, all right. Now, here's what's important in this situation, and in all polynomials, all right. There's something called the fundamental theorem of algebra. And you would think it would be something really kind of earth-shattering, but it kind of really isn't. What it says is that the degree of a polynomial, is the number of solutions the polynomial has. So if we have a third degree polynomial, we know it's going to have 3 solutions. A fourth degree is going to have 4 solutions. A fifth degree is going to have 5 solutions. Quadratic has 2 solutions. All right. The fundamental theorem of algebra tells us how many solutions we're going to have. All right. So everything that we've done so far has been a third degree. We had 3 x-intercepts. They were nice and clean. Everything was great. All right. The fundamental theorem makes sense to us. That's what we're going to have. All right. But when we look at this one right here, okay, here we only have 2 x-intercepts, but this one is a multiplicity of 2, which means that it's a double root, so it counts as twice. Because remember, whatever that number is, say it's a 2, then when we write that, that's going to be x minus 2 squared. because it's a multiplicity of 2. So it counts as 2. So still, the fundamental theorem works, right? Because we have 1 there, and we count that one as 2. All right? We'll get to this pink or fuchsia, or whatever color that is, in a little bit. So here's another one I want you to solve. So we're going to go negative 2x to the fourth. Uh-oh, now we're going to do a fourth. Plus 6x to the third. All right, minus 2x squared minus 6x plus 4. All right, equals 0. Now, so if the fundamental theorem is right, then how many solutions should this have?
3, 4.
4, right? It's going to have 4. Well, go graph them and see how many you find.
Sorry, I couldn't find that home key that you're talking about for the viewing window.
So do you see where the little, you see where the wrench is, right? The tool?
Yeah.
And the plus and the minus?
Mm-hmm.
Well, that the home key's underneath that. Now, if it's not there, then that means you're already in the standard window.
Oh, okay.
Okay, so then I wouldn't mess with it. You should be able to see your x-intercepts from there.
Perfect.
I'm only seeing 3 x-intercepts.
Okay, so tell me about those. Is there one that's...
I have negative 1, 1, and 2.
Okay. Is anything happening special at any one of those x-intercepts?
Nothing crazy.
Nothing crazy. Does it ever...
a multiplicity.
Which one has a multiplicity?
1.
So that one, remember, if it's coming down and touching and bouncing off, that's a double root, so that counts as 2.
Okay.
Okay?
So, okay, then I have 4.
I'm glad you brought that up. So here's our answers, okay? And even though you say, hey, there's only 3 x-intercepts, but the 1 is a double root, so it counts as 2. So then when we wrote this in factored form, we'd have x plus 1, x minus 1 squared, and x minus 2. Okay, now remember this negative 2 is going to slide out in front of that, and that's what that would look like in factored form, but these are our answers. And we don't have to write 1 twice. It's already there. All right, so we don't need to write it twice. But that's what's happening, okay? So when you're solving these, we're graphing them first every single time, finding the x-intercepts and going from there. All right? So far so good? All right, I'm still going to go here. Okay, so now I'm going to give you this one. We're going to go back to a cubic here, our third degree. So we have this. Oh, no, hang on. Not that one yet. Hold off. Sorry. Here. We're still going to go back to the third degree, but it's a little different. Plus 3x squared plus 3x minus 5 equals 0. Okay. Again, graph it. Let's find some x-intercepts. Those are my answers. We'll see who gets it first this time. Fiona was on. Oh, Russell got this one. Uh-oh. Okay, negative 1.449. 1 and 3.449. Okay, so, hey, it had 3 of them, but see these? Those are not exact. Those are approximate solutions. So even though, yes, they are them, we cannot really use those. All right, but we are going to use this. Okay, here's how we're going to do this. So we're going to take this and we're going to use some synthetic division. So now I'm going to go negative 1 and 3 and 3 and negative 5, right? Do some synthetic division on this. Negative 1. Okay, negative 1, that's 2. 2, that's 5. 1, 5, 0. We know we're going to get 0 there. Now, when you're doing this, okay, and you know that this is an x-intercept and you don't get 0 there, something's wrong. Because you know that it's going to go in there nice and evenly. All right, so you got to have a 0 here. That's a good thing. Now, what does that mean? So what? Well, here, look. Remember we talked about how when we're dividing, we're reducing it down? So now we've reduced this down to a quadratic, right? So in factored form, it would look like this. So that means that if we were to FOIL these, right, we'd end up with what we started with. So what we want to do now is take and solve this part, okay? But it's a quadratic. So we just use the quadratic formula on it. How about that? That's exactly why we reviewed it.
I'm sorry, I'm just really confused still on how you get that second part of the factor form.
So we started out, that's okay, so we started out with this third degree, correct?
Yes.
So then we said we found an x-intercept, it's 1. So we divided this by x minus 1. Okay, by just using synthetic division with 1. So when you do that, you're taking this x cubed, this third degree, and you're dividing it by x minus 1, which gives us a second degree. So synthetic division, all right, is an alternative to, here, let me get this over here, x, what was it, was this one, negative x to the third.
Okay, I'm kind of understanding it now. I see, I get it.
Yeah, because see, you're dividing this by x minus 1. So when you divide this long division-wise, that's where the x squared comes in, because x squared times x gives you that. All right. Okay.
Thank you.
Yeah. No, good. All right, yeah. So here we go. So now we're going to put this, right? We have negative 1, 2, and 5. So, did I do the right? Oh, this is supposed to be a negative. No, that's right. Did I get it right? Yeah, okay. I'm no nervous. Oh, no, it's good. I see. All right. So the opposite of b, so it'd be negative 2 plus or minus square root. Now, I like to take the 2 and square it. So like that. Minus 4 times negative 1 times 5 all over 2 times a. A is negative 1, so that'd be a negative 2. So that's what I got. All right. A is negative 1, so that's negative 2. Okay, so here I'm going to go negative 2 plus or minus square root. I get a negative 4 times a negative 1, which is a positive 4 times 20. So that's going to be a plus. I get negative 2, nothing changes there. Negative 2 plus or minus the square root of 24 over negative 2. Now this one, again, you can reduce it. All right. Now what do I mean by that? Well, this probably is something that you might remember, but most likely not. So here I'm writing down our perfect squares. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. So what I'm going to do is take this 24 and I'm just going to rewrite it in terms of 4, because it's a perfect square, and 6. 4 times 6 is 24. So I always want a perfect square, because now I can take the square root of that, and that 24 becomes 2 root 6. All right? So now I can take that 2 and go into all that stuff and, oops, and get that, okay, as my answer. So, is this wrong? No. But remember what I was telling you with the 6/8 and the 3/4. It's just a different answer. This is simplified. This one is not. All right. Does it change anything? No. You're still going to say, oh, here's my solutions. My solutions are 1, comma, -2 plus or minus square root of 24 over -2. Those are my solutions. But if I write this in factored form, okay, it gets a little messy, because then I would have to put a minus here and put a -2 plus the square root of 24 over -2, okay, and an x minus -2 minus the square root of 24 over -2. So it gets a little bit messy in terms of writing it out in factored form, rather than just putting 1 plus or minus 1 plus 6 and 1 plus or 1 minus the square root of 6. So it really doesn't bother us as far as the solutions go. But if we have to write it in factored form, kind of yucky there, right? It's kind of nasty. All right. So that's why you'll see it being reduced in some of the things that you do. All right. But that's how you solve these. Okay, so if we only have one x-intercept, we know that there's 2 more. So we're going to use the quadratic formula to break that down. Questions on that part? Okay. Now we're going to try another one. All right. So we're going to go negative x cubed plus an x squared minus a 2x plus a 2. All right, equals 0. Okay, go graph that one and give me an x-intercepts. One. Good. The only one it has is 1. Uh-oh, wait a minute. Well, fundamental theorem of algebra says we got to have how many?
3.
3. But we only got 1. Well, let's divide it. So we're going to take this 1, right? And we're going to divide it in. So we have -1, 1, -2, 2. And we use synthetic division. So 1's going to go in there. I'm going to get this -1, drop it down. Put a -1 there. That's 0, 0, -2, -2. There's the 0 that I want. All right. So even though I only had one x-intercept, this is that other case where I drew that only one x-intercept. What are we going to do now? Situation. Here's what we got. All right. So we're going to put this in here, and we're going to work it out. All right. So we did this, and now we're left with a quadratic, right? So here's my quadratic here. So negative x squared, I don't have an x, minus 2 equals 0. So what we're going to do is solve this. Now, in this particular situation, all right, you can use the quadratic formula. It's not the wrong thing to do. But it's easier to just straight up solve this, because all we got to do is add a 2 to both sides, divide by a negative 1, and get that. Okay, so I'll stop for a second so you can see kind of what we did there. Okay, so now all we got to do is square root, right? But we have a problem, because we can't take the square root of a negative number. All right, can't do that. So that means that we have an imaginary solution here. Okay, and so again, I don't know how many people are familiar with imaginary solutions or imaginary numbers. All right, the imaginary number I is equal to the square root of negative 1. All right, so when you have a square root of a negative, it doesn't have a real answer solution, but it has a complex answer solution. The complex numbers are all real numbers and imaginaries. So it's all the reals, every number you can think of, and these little I terms. Okay, that's your complex number system. So when we're solving these polynomials, all right, you're solving them over the complex number system, which means you could have some imaginary numbers as solutions. If that's the case, then this is just going to be x equals plus or minus I square root 2. So what happens is that the negative pops out on the outside, or comes to the outside and becomes an I. Right? Because I is equal to the square root of negative 1. So if we rewrote this thing here, we could rewrite it as the square root of negative 1 times the square root of 2. And the square root of negative 1 is I. So really all that happens when you have a negative is that the I is going to pop out in front, and that's what you get. X equals plus or minus the square root of 2, I square roots of 2 in that situation. All right, so that gives us our three answers. All right, 1 and plus or minus I root 2. Okay, so now you know when you see a situation like, and I'll come back to that part, when you see a situation like what we had way up here, if I can find it, that I drew them out at. Oops, oh, there it is. Okay, so when we have a situation like this fuchsia one right here, okay, here's one answer, but that's the only one I got. So the other two are imaginary, all right? And the same thing happens with the fourth, all right? If we have a W, and remember we talked about this, if we have a W and our W has 1, 2 x-intercepts, that's only two answers. The other two have got to be imaginary. Okay, they got to be imaginary. So that's where that's coming from. All right, that fundamental theorem says whatever the degree is, that's what your number of your solutions are. Okay, but what it doesn't necessarily specify is that they are complex solutions, not real solutions. Okay? Okay. So let's continue with this just a little bit. One of the other things that goes along with that fundamental theorem of algebra is that in complex solutions, okay, in complex solutions, if a plus bi, so that means if one number is imaginary, then a plus bi is a solution, then a minus bi is also a solution. Now, what does that exactly mean? We got a and b, and what the heck are we talking about? So up there, we had plus or minus I square root 2. All right? Well, if I tell you that, hey, I have a polynomial and 1 plus the square, 1 plus 1 plus I root 3 is a solution. Okay? And it's possible to get that. Okay? It's possible to get that in a quadratic formula. Then what you automatically know is that 1 minus I square root 3 is a solution too. Now, somebody, and I don't remember who it was, pointed out one time that if negative 1.2 something was a solution, then is positive 1.2 something a solution. So see how they're going to be, one's going to be plus and one's going to be minus? Because that comes from this part of the quadratic formula where you have a plus or minus. Okay, so if one part's a positive, then yes, the other part's a negative. That's particularly in the cases of complex numbers. Not necessarily the truth when it comes to just specifying reals. It depends on what b is, because you could just have two positive solutions there. All right, but in this case, when you have an imaginary and one's negative, then you know the other one's positive and vice versa. Okay.
I think I know the answers to this, but that means that for I problems, there's always two answers.
Yeah. Yes. Yeah. So anytime you have, so yeah, I mean, you could have a situation like this where we just have a second degree, right? And one answers might be, it might be 2i, okay? You know automatically that negative 2i has got to be the other solution, okay? You got to have two imaginaries. You can't just have one. Okay, good question. We've pretty much examined every single situation with solving except for this last one. Okay, so let's do this one. 3x to the fourth minus 3x cubed minus 12x squared plus 3x plus 9. Okay, equals 0. Go solve it. Let's find x-intercepts. Okay. So you notice on top of the game again, -1 and 1. Okay. Again, notice how we have a -0.303 and a 2.303. Those aren't exact. They're not going to help us. All right. So we got to do synthetic division. So let's pick one of these x-intercepts to do synthetic division. So somebody go ahead and throw one out there, -1 or 1. Which one do you want? 1. Okay, good. Here we go. 3, -3, -12, 3, and 9. Okay, go ahead and do it, and then somebody can chat it or tell me what the bottom row is going to be. These guys right here. Okay, so we got 3, 0, -12, 27, and that one's got to be 0 somehow or another. Or is it, what do we got here? That can't be. I must have something wrong here. 3.
I believe the second one's -6.
0, -12. Yeah, something's here. Here we go. So this is 3. 1 times 3, that's 0, 0, -12, -12, -9, -9, and 0. Yeah, that's okay. We got it. All right. So now we got this. Okay? But look, this is a third degree. Doesn't do us any good. What should we do now to get us down to a quadratic? But we're going to do it with these numbers. Well, not the 0. Just these numbers. What can we do? We have a third degree now, but we need to get it down to a quadratic, second degree, or quadratic. Don't we have another x-intercept? Ryan, we could maybe a third. It's really hard to factor a third degree and get it down to that. But we do have another x-intercept, right? So what can we do with this to get it down to a quadratic? We could do synthetic division again, right? Because remember, we have another x-intercept. We still have -1, all right? We still have that. So we use synthetic division again, all right? We know we're going to get a 0, and there is our quadratic, okay? And we can use a quadratic formula, right? So we're going to get +3 plus or minus 9, because that's 3 squared, minus 4 times 3 times -9, all over 6, 2 times 3. And I'm going to keep working this out. 4 times 3 is 12, times 9 is 108. 3 plus or minus the square root of 117 over 6. I finally get a nasty one. I can't even reduce that. Okay. So there's my answer along with 1 and -1. So you're going to have 4, right? They're all 4 reals. There's no imaginaries there. But when you come up with a situation like that, you got to do synthetic division twice because we can get it down that quadratic, and then we're good to go. All right. So that's how those are done. Okay. That's every scenario that we have. All right, for solving them. So that's 3-2 and 3-3. Now 3-2 is only real numbers. You're not going to have imaginaries. You just graph them, find the x-intercepts, do synthetic division, be done with it. On 3-3 is where you're going to have a little bit more stuff. So I want to stop this for just a little bit, and I want to share this, and I want to go over some of these. Okay? So I want to talk about what these questions are asking you to do. So right here, okay, it says for problem 7 through 16, okay, information is given about polynomial functions, whose coefficients are real numbers, find the remaining zeros of f. Here's my deal. I have a degree of 3. Here's 1 0, 3. Here's another 0, 4 minus I. Automatically, I know that 4 plus I has to be the other 0, right? Because if 4 minus I is 1, then I know 4 plus I is 1. That's all it's asking us to do, is to tell me or tell them what the other 0 is, okay? Every one of these has an imaginary in there, so you know that it's got to be the opposite. Those are called conjugates, by the way. They call those complex conjugates when one is minus and one is plus. Okay.
Sorry, I think I missed it. Is it plus or minus 3, plus or minus 4?
So it's 3 and 4 minus I, okay, and 4 plus I. So it's always going to be the opposite sign of this. So this is 4 minus I. We're going to get a 4 plus I. Okay?
Oh, okay. Thank you.
Yep. All right. I'm going to keep going through here. 17 through 20. So it says, form a polynomial with real coefficients having the given degree and zeros. Answers will vary depending on your coefficients. So here's a situation where you're going to write these in factored form. It doesn't specify which way to write it. The degree is 4, so I should have 4 zeros. Well, there's 1. Okay, here's 4, but it has a multiplicity of 2. So that means, I'm going to have an x plus or x minus 4 squared there because the multiplicity is 2. All right. So then what are my other ones? Well, I have here, let me get this eraser because I don't want that there and I don't want that there. There we go. So now I got to use this 3 plus 2i. So I'm going to go over here and go x minus and put it in parentheses 3 plus 2i. Okay, and then my other one is going to be x minus parentheses 3 minus 2i. There again, it's hitting on that idea. Okay. All right, so x minus 4 squared, multiplicity of 2, x plus 3i, x minus 3 minus 2i. We don't do anything with it. We leave it alone. They might have you FOIL that, but you don't need to. You just leave it. All right? Just leave it alone. So that's those ones. Down here in 23 through 27 through 30, okay, which is in this section, use the given zero to find the remaining zeros of each function. So notice that it gives you a cubic here, or third degree, and 2i as a zero. Well, that means that negative 2i is also a zero, but we still got to find one more because, you know, we have to get it so that there's 3 of them, right? All right. So let's see what we can do here. So we can approach this in a couple different ways. So if we have x cubed, okay, minus 4x squared, okay, plus 4x, all right, minus 16, all right, I'm going to do synthetic division, but I'm going to do it with 2i. Now this is going to get, oh, wait a minute here, hold on. I don't want to put all that junk in there. I just want to put in the, so I'm going to go 1, negative 4, I don't know why I was writing it all out, 4, and negative 16. There we go. Okay, so I'm going to do synthetic division. Here we go. 1. This is going to be a 2i. Uh-oh, man, this is going to be messy. How do I handle that? Well, you go ahead and treat the I as if it was a variable, like an x. So we have a negative 4 minus, or no, plus, sorry, 2i. Okay? All right, so I'm just adding these. Right, now I'm going to multiply 2i times this. So I'm going to get a negative 8i. Okay, I want to move the 16 over a little bit. Get rid of it. Move it over here. Minus. Okay, so I got an 8i. 2i, I'm going to go up here. 2i times 2i is 4i squared. Remember, we're treating it like a variable. Okay. Well, here's what happens in this situation. Because I is equal to the square root of negative 1, the square root of negative 1 times itself is going to be just negative 1. Because this square root is going to go away, and that square root is going to away, and leave me with negative 1. So when you multiply two square roots, they cancel each other out. So I squared is negative 1, which means that this is just simply negative 4. All right? So now I have this minus 4. Okay? Now that I have a minus 4 here, remember that 2i gives you negative 4. That 4 goes away, leaves me with negative 8i. Okay? Times that by 2i, look what happens. I get 16 and 0. Okay? So, big deal. That's a mess. What do I do with that? Well, we have to do synthetic division with this guy, but with negative 2i. Okay? So, negative 2i. Now, what we could do, all right, is we should have maybe graphed this and see if it had a nice x-intercept. That's one of the things I didn't think of. So, we could have graphed this and checked to see if it had a nice x-intercept, and we wouldn't have to be doing this. So let's go back and do that. So graph this guy and see if it has a nice x-intercept. Because I'm not exactly sure how they're going to do these. Okay, but this is how you would do it. So maybe they do have nice x-intercepts. I'm not 100% sure of that. So let's graph this and see. My guess is that there might have some nice x-intercepts and we don't have to divide these. Because this is kind of messier than I thinking they're going to ask you. It has a nice x. Good. So there's our answer. 2i, negative 2i, and 4. I don't think you're going to have to go through the synthetic division part of this and do it with I terms. I think it's all going to work out. Okay. I think it's all going to work out. These ones you are just solving, so that's not a big deal. All right. We just did 4 of those. Okay. So that's how you got to do this. I want to hang in there with me here. I want to show you some stuff. I want to show you what your next project's going to look like. Oops, nope, I didn't want to do that. And I can best explain it to you by showing you some examples. Where are they at here? Project 2. Okay. I am going to share this screen. So our next project is going to be where we're going to create some art here using Desmos. And we are going to use polynomials to do that. Okay. So what this person did was they made a bear. Now, most of the time you can get an image, but they just did it free-handedly. So here, oh, I guess this is a screenshot. Let me see if they have the, here we go, the actual link here. So these are folders, and I want to show you how to create those. Not tonight, but I will. So here are some of the equations that they used to make the stuff. Okay, there's the image. She did have an image. So there's her image. There's the back, the ears. So everything is broken down into folders. All right, the back legs and so forth. All right. Let me go back and show you another one. Let me get rid of the bear. Yep, leave it. And let's see. This one's pretty good. I keep forgetting to get the Desmos link. It's just kind of a little scene here. There's a flower. Bumblebee. Flower. And flower. Okay, if we turn that off, you can see it's turning that part off. Okay, let's go find another one. I'm just kind of guessing on these here. I don't know what they look like. Oh, let's look at this one. There we have. There's the image. And that's what they did. So let's turn the image. All right, so here, now they didn't use folders, so that's one of the things. They got a lot of different things here you're not supposed to use, but I want to show it to you anyway as an example of some things you could do. I don't remember what this one looked like. Here we go. Looks like we got sort of a cat here. Head, tail, body. So the idea is that we're going to create some art using Desmos. All right. I'm going to go find it for you and show you where it is. Let me get rid of this and this and this. Nope, and this. Oops.
Are we doing the quiz on Wednesday instead?
Yeah, I don't know. Well, probably. I'm gonna look at that and I'll make you guys an announcement. Okay. It looks hard, but it's not as bad as you think. Oh, here it is. So it's up and posted for you. Okay. And it gives you some links to some Desmos things, and I can show you some more later when I actually show you how to do this. So it's up here. Okay. This is how a rubric that's going to be used to grade it. The thing is that when you're finished, you're just going to send me a link, but you can only use the functions that we've done. So polynomial, exponential, logarithmic, and rationals. You can't use circles. You can't use ellipses. You can't use any drawing tools. You can only use functions. Okay. So really, this isn't due till 323, right? I don't know why there's an AM there. We'll get rid of that. All right. And this is the rubric how we're doing it. They also have a little link that you can check out. Those are really complicated, but they're good ones to look at too. All right. And I'm going to show you how you come up with these designs and how you make them. So the thing you can do from now to start thinking about it is think of something you want to do. You know, cartoons, characters are good things to do. Animals are good things to do. But don't find anything that's going to be too hard. All right, because you're just not going to have enough time to get it done. So be careful on the detail. What I would suggest is see if you can find something you might be interested in. Shoot it to me by an email and say, hey, is this a possibility? And I will be straight with you and say, yeah, you can do that. Or I'm going to say, I don't think you're going to be able to do that. All right. What you'll find is once you get into it, you'll kind of get into it, and it's one of those things that's kind of hard to stop. It's really kind of addicting, kind of different. You wouldn't think so, but it is. All right. I'll look at the quiz thing. We might not have it at all if we can't fit it in. All right. I wanted to get this project shown to you, and I want to show you how to do it, so we for sure do that on Wednesday. I'll figure something out and put an announcement. Look for an announcement tomorrow on that, and maybe what will change. So, again, I'm okay because we have a little bit of time. I just wanted to make sure I did that. All right. It's definitely time for 8:20, so it's time for me to end this. You're all set for 3-2 though and 3-3, so you can work on 238. We'll just push 2-3-4. None of the due dates are going to change on our assignment, so we should be okay on that. All right, for now. So thanks for hanging in there. Have a good rest of your evening, and see you on Wednesday.
Thank you.
No quiz tonight. No quiz tonight.